Hello everyone, I am Dr. Naresh Kumar, Assistant Professor from the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on 180 degrees conduction mode of three-phase inverter. Now here in the previous lecture we have covered in the voltage source inverter, single phase, half bridge and full bridge inverter. In that R load, L load, RL load, RLC load, in that XL is greater than XC and XC is greater than XL. For the same for full bridge inverter. Here three-phase inverter, the working of three-phase inverter, there are two possible modes. Here first one is 180 degrees conduction mode and second one is 120 degrees conduction mode based on the time length of each switch. Here in a 180 degrees conduction mode, each thyristor conducts for 180 degrees and in the 120 degrees conduction mode, each thyristor conducts for 120 degrees. Let us talk about 180 degrees conduction mode. This is the circuit diagram of 180 degrees conduction mode. In this, we have total 6 thyristors T1, T2, T1, T2, T3, T4, T5 and total T6, total 6 thyristors, 3 legs, 1, 2, 3 and 2 groups, upper group and lower group, and 1 DC source and 1 load. Here total 6 thyristors T1, T2, T3, T4, T5, T6 and leg 1, 3 legs, we can call it as wings, arms, segments and leg 2, leg 3. In that leg 1, T1 and T4, in the leg 2, T3 and T6 and leg 3 and T5 and T2. In the single phase half bridge we have only 1 leg, in the full bridge we have only 2 legs, in this we have 3 legs. And upper group switches are denoted as T1, T3 and T5. Switches means thyristor here, and T4, T6 and T2 are lower group switches. And that entire setup is given to the DC voltage VDC, and this load is connected across this one. So star load I have given. Here we have 6 assumptions. The working of 180 degrees conduction mode of 3-phase inverter. Here the first assumption is for the simplicity, snubber circuit and commutation circuit have been omitted. And next, second one is the load may be either star or delta. The load connection may be either star or delta. And next, third one is here in the same leg, at the same time, in the same leg, 2 thyristors should never be closed. T1 and T4, T3 and T6 and T5 and T2. In the same leg, both the switches, both the thyristors should never be closed circuited. So that may leads to the battery short circuited. That may failing the entire setup. All the time it should be avoided. And next, each thyristor conducts for 180 degrees. And next, here each thyristor conducts for, here T1 is conduct for in the first leg and 180 degrees and T4 is conducts for another 180 again, and T3 is conducts for 180 degrees, and next here T6 is conducts for another 5 degrees and T5 is conducts for 180 degrees and T2 is conducts for 180 degrees. Next, in order to get the 3-phase balanced output voltage at the output terminal, so here each thyristor, so in the upper group switches, T1, T3 and T5 conducts at an interval of 120 degrees in order to get the 3-phase balanced output voltage. Because we are dealing with 3-phase, we needed the output side 3-phase balanced output voltage. Here we are dealing with 3-phase output voltage. First T1 starts at 120 degrees and 120 degrees and T1 starts at 0 degrees and T3 starts at 120 degrees, and T5 starts at T1 starts at 120 degrees, and T2 starts at 0 degree. T1 starts at 0 degrees, T2 starts at 120 degrees, and T5 starts at, this is T3. T1 starts at 0 degrees, T3 starts at 120 degrees, and T5 starts at 240 degrees. So these are the upper group switches. Same for lower group switches. And next, here at the same time, at any given time, so 3 switches will conduct. So 1, 2, 3. So 2 may be from upper group, 1 and 1 is other lower group R, and 2 may be from the lower group and 1 from other group. At any given time, so 3 switches will conduct during this. So at 0 to 60 and 60 to 120, at any given time, so 3 switches will conduct. Here in the 0 to 60, T1, T6, T5 conduct, and 120 degrees, T1, T6 and T2 are conduct. Now let us see the operation, the control scheme. How we can control let us understand how control scheme for 180 degrees conduction mode, how we can control each switch. Here T1 starts. So here this is for leg 1, this is for row 2 for leg 2, and row 3 for leg 3. Leg 1 thyristors are T1 and T4, and leg 2 thyristors are T3 and T6, and leg 5 thyristors are, leg 3 thyristors are T5 and T2. And here, so T1 first, T1 turn on at 0 degrees case. So it conducts for 180 degrees. T1 starts at 0 degrees, firing at 0 degrees, it conducts up to 180 degrees. And remaining 180 degrees duration, and T4 will conduct. T4 will conduct. So remaining 180 degrees, T4 will conduct. And next, in order to get 3-phase balanced output voltage, here T3 must be starts. So T3 must be starts. So upper group switches conducts at an interval of 120 degrees. So that we discussed in the previous slide. So T3 starts at 120 degrees. Next, and this T3 duration is 180 degrees. 120 plus 180 is 300. Next, remaining 180 degrees duration, lower group switch, T6 will conduct. T6 will conduct. So T6 remaining 180 degrees. So 240 plus 180. So here 60 and again 60. And in order to get the balanced 3-phase output voltage, T1, T3 and T6 at, so this is for T3 and this is 0 for T1 and T3 for 120, and T5 for upper group switches conducts 120 degrees apart. So now here T5 starts at firing at 240 degrees. So this time length duration is here 60 and here 120 and here 60, total 180 degrees. Here remaining 180 degrees, so T2 will conduct. Remaining 180 degrees, here T2 will conduct. So this is the control scheme for each switch at regular interval of time, a 60 degrees duration. Now here the switches are programmed to turn off and turn on here in order to get the 3-phase balanced output voltage at the output side. Now here T1 and T4, T6 and T3, T6, T5, T2 and T3. In between 0 to 60 degrees case, T1, T6 and T2. So in order to be here, from 0 to 60 degrees case, so here T1, T6 and T5 thyristors SCR switches will conduct. Now how we can draw the, here only remaining switches will be turn off, open circuited. Here what are the T1, this is T1, T6 and T5 thyristors will conduct. And next this is connected to this one, and this one is connected to this one, and this one is connected to this one. This is the equivalent circuit. How we can draw the equivalent circuit for this one? This is the equivalent circuit. So now here this is A, this is C, and this one is the B. Now here using voltage division rule, we can determine here phase voltages. Here VAN voltage and VCN voltage and VBN voltage or VNB voltage. Now here how to simplify this one? So these two are connected in parallel and with same impedance. So Z1 into Z into Z by Z plus Z. That value equals to Z by 2. This equivalent impedance is Z by 2 and this 2. So now here this equivalent impedance equals to Z by 2 by Z by 2 by 2 plus Z by 2. So now here I am applying voltage division rule. So this voltage entire impedance equals to this impedance equals to Z by 2. This impedance overall, this impedance Z by 2. This overall impedance is Z by 2 and this one is Z. So now how we can determine VAN value using, this is total voltage, these two are VAN and VCN are same because in the parallel circuit same voltage developed across the each element. VAN equals to VCN, and here VAN equals to this supply voltage into same branch impedance Z by 2 divided by Z by 2 plus this Z. So now if you simplify this one, that value equals to VDC by 3. Now here VAN equals to VCN equals to same voltage developed across each element. In case of parallel circuit, VAN equals to VCN equals to VDC by 3. Now what about this VNB? VNB equals total voltage minus this VAN or VCN. So this is VDC minus VDC by 3, that is VNB. VDC minus VDC by 3, that is 2 VDC by 3. But here we need only VPN only. Here we got VCN, VAN and VBN. So VBN equals to minus of VNB. VBN equals to minus of VNB, that equals to minus 2 VDC by 3. Now we got during 0 to 60 degrees case, T1, T6 and T5 will conduct. So the circuit T1, T6 and T5 will conduct. The equivalent circuit, it looks like this. So for this case, so the phase voltages, the values are VDC by 3, VCN equals to VAN equals VDC by 3 and VBN equals to minus 2 VDC by 3. Next, between 160 to 120 degrees case, in between these two. So now here in this case T1, T6 and T2 thyristor switches will conduct. So during 60 to 120 degrees, T1, T6 and T2 switches will conduct. So now T1 will conduct, next T6 will conduct and T2. So two lower group switches and one upper group switch will conduct. So that is T1 in from the upper group, and T2 and T6 switches will conduct from the lower group. So now draw the equivalent circuit. This is for this one and this is for this one and this is for this one and this one. How we can draw the equivalent circuit? This is the 2 from lower group. So this is B and this is C and this one is the A. Now same, determine the phase voltages for this particular case during 60 to 120 degrees when T1, T6 and T2 thyristors will conduct. So now this is Z and this equivalent impedance is Z by two parallel impedances, same impedance means that is Z by 2. Now here voltage division rule, if you apply for this Z by 2 and Z, so VDC VAN VAN equals to, first determine this one, VAN equals to the same branch impedance into supply voltage divided by total impedance Z plus Z by 2. So that equals to VDC by 2 VDC by 3. Next, how VNB and VCN equals to VDC minus 2 VDC. VDC minus 2 VDC by 3, that is VDC by 3. But here this is VNB and this is VNC. We need VBN and VCN, that are phase voltages. So VCN equals to VBN equals to minus VDC by 3. Next, between 120 and 180 degrees case, T1, T3 and T2 switches will conduct. So here between 180 to 120 to 180, T1, T3 and T2 switches will conduct. T1 will conduct and T3 will conduct. Next T2 will conduct. Two switches from upper group T1 and T3, and low from the lower group only one switch, that is T2. Now draw the equivalent circuit. And next here, this is the equivalent circuit. T1, T3, T2. So one lower group switches. Now here, this is the equivalent circuit. So now this is A, this is B, and this one is a C. Now determine this equivalent impedance is Z by 2. So now this Z by 2 voltage VAN and VBN same voltage. So now VAN equals to VDC into same branch impedance VZ by 2 by Z plus Z by 2, that value equals to VDC by 3. Now same way VAN equals to VBN equals to VDC by 3, same voltage. And next VNC equals to VDC minus VDC by 3, that equals to 2 VDC by 3. Now here we need VCN, but so here VCN equals to minus VNC equals to minus 240 VDC by 3. Next, during 180 to 240, T4 thyristor, T3 thyristor and T2 thyristors will conduct. T4, T3 and this is T2 and this is T4. So T4, T3 and T2. T4, T3, or you can draw like this. Now here T4, T3 and T2. This one. Now here same Z, this impedance is Z by 2. VBN equals to, this one is B and this is A and this one is C. This VBN equals to this same branch impedance into total voltage divided by Z plus Z by 2, that equals to 2 VDC by 3. Next, VNC and VCN equals to VDC minus 2 VDC by 3, that is VDC by 3. But here we need VAN and VCN. So for this case, VCN and VAN equals to minus of this one. minus VDC by 3. Next, during 240 to 300. During 240 to 300, T4, T3 and T5 thyristors will conduct. T4, T5, T5 and T6, these two. This is the equivalent circuit during 240 to 300. T4, T3 and T4, T4, T3, T4, T3, this is T4, T3 and T5 thyristor will conduct. This is B and this is C and this one is the A. So same thing here, VBN equals to same value. This is Z by 2. Next, VBN equals to VBN equals to VCN equals same VDC by 3. And next VAN equals to VDC minus VDC by 3, that equals to VDC by 3. But here we need VAN, that equals to minus 2 VDC by 3. Next, last one, T4, T6 and T5 thyristors will conduct. T4, T5 and T6 thyristors will conduct. So draw the equivalent circuit diagram. This is the equivalent circuit diagram. This is C and this is A and this one is the B. So from this determine VAN, VBN and VCN. So same procedure for all cases. Now if you observe in this, so each thyristor conducts for 180 degrees. T1 conducts for 180 degrees, T4 conducts for 180 degrees, T3 conducts for 180 degrees and T6 conducts for 180 degrees. And next, T5 conducts for 180 degrees and next T2 conducts for 180 degrees. Each thyristor conducts for 180 degrees. Next, in the same leg, one thyristor conducts for 180 degrees and in the T1 conducts for 180 degrees and T4 conducts for 180 degrees. Next, in order to get the balanced output voltage, each thyristor from the upper group switches conducts at an interval of 180 degrees. Upper group switches are T1, T3 and T5. So one starts from 0, 120 and 240 degrees. Same for lower group switches T4, T6 and T2. First case, each thyristor conducts for 180 degrees and upper group and lower group switches conducts at an interval of 120 degrees, and at any given time, three switches will conduct. Three thyristor will conduct. At any given time, three switches will conduct. So these are the three important points. In this way, we can control the programs are switched to turn on and turn off in order to get the three-phase balanced output voltage. Now, here these are the phase voltages during 0 to 60 degrees, and next during 60 to 120 degrees, VAN, VBN and VCN phase voltages, and during 120 to 180 degrees case, during 180 to 240 degrees case, we derived in the previous slide. And next 242, 300 degrees case. Next 300 to 360 degrees case. Now plot the phase voltage waveforms. Here, this is the control scheme to turn on and turn off. Programs are switched. Switches are programmed to turn on and turn off T1 and T2, T3, T4, T5. Now, this phase voltage we got from the previous slide. Now here, if you draw the phase voltage, this is omega t, and omega t. So these are the VAN, VBN, VCN. Now here, according to this numbers, you can draw the waveform. Now here, VAN equals to, this is VDC by 3. VDC by 3. This is minus 2 VDC by 3. And next here, this is VDC by 3. And next, same way during 60 to 120. During 60 to 120 degrees case, 2 VDC by 3. And next here, minus VDC by 3. Minus VDC by 3. Let me change the color over here. This 120 degrees case, VDC by 3. And next VDC by 3. And this one is the minus 2 VDC by 3. Next, during 180 to 240, so minus VDC by 3, VDC by 3, 2 VDC by 3, and minus 2 VDC by 3, minus VDC by 3. Next, 240 to 300, so minus 2 VDC by 3, and next here VDC by 3, and here VDC by 3. The last one, minus VDC by 3, this one, and next minus VDC by 3, and next 2 VDC by 3. In this way we can plot the phase voltage. And here, what about the line voltage? Line voltage equals to VAB, VBC and VCA. Voltage at the terminals. So now here VAB equals to VAN minus VBN, and VBC equals VBN minus VCN, and VCA equals to VCN minus VAN. So now we have VAN, VBN, VCN. Then we can determine the line voltages VAB, VBC and VCA. So now let us plot the phase line voltages. These are the phase voltage diagram. So line voltages, same thing here. So during VAB, VBC, VCA are line voltages, VAN, VBN, VCN are the phase voltages. So during 62. Now VAB equals to this one VAN minus VBN. So this is VAN minus VBN. So now here how this is VDC by 3, this is minus 2 VDC by 3. VDC by 3. So VDC by 3 minus of minus VDC by 3, that is VDC. Next, here this is VDC, 2 VDC by 3, this is minus VDC by 3. 2 VDC by 3 minus of minus 2 VDC by 3, this one is also VDC. And during this period 120 to 180 degrees case, this is VDC by 3 and this one is a VDC by 3. That value is 0. Same way here, this is minus VDC by 3, minus VDC and this is minus VDC, and this one is a 0. Subtract from A to B, VAN minus VB, if you do this one. Same way here, VBC equals to VBN minus VCN. So this one minus this one, this is VDC by 3 minus VDC 2 VDC by 3 minus VDC, that is minus VDC. Minus 2 VDC by 3 and minus VDC by 3, that is minus VDC. Same way here, BC, this one, these two, this value is 0. This minus VDC by 3 minus VDC by 3, this value is 0. Next here, these two, VDC by 3 minus 2 VDC by 3. So this value is VDC. Same here, do the VBN minus VCN. Next, VCA means VCN minus VAN. So now here VCN, this is VDC by 3, VDC by 3, this value is 0. And next, this value equals to VDC by 3, 2 VDC by 3 minus of this VDC by 3, that equals to minus VCN, this one minus VDC by 3 minus 2 VDC by 3, that is minus VDC up to here. Next here, this one minus 2 VDC by 3 minus VDC by 3, that is minus VDC. Same way, determine this one, this during this period. This is phase voltage waveform. These are VAN, VBN, VCN, and these are the line voltage VAB, VBC, and VCA line voltage waveforms. Now, this is phase voltage waveform, and that magnitudes are VDC by 3, 2 VDC by 3, and this is VDC by 3, and minus VDC by 3, minus 2 VDC by 3, and VDC by 3, minus 2 VDC by 3. So now if you determine RMS value, how you will calculate the RMS value? Square, this is the symmetric waveform. So here for this case, square the waveform, take the average and take the under root. So now here, square the waveform during this period 0 to 60 degrees. So this time period is pi by 3, and this time period is pi by 3, and this time period is pi by 3. So total time period, this period is pi by 3. Total time period is 2 pi. If you do the half, this is half wave, this is symmetric waveform. So up to here pi. So for the symmetric waveform case, so here during first half here pi by 3, pi by 3, pi by 3, square the waveform. If you do the square the waveform, and next square the waveform, this should be positive, and here you can determine, only take half cycle RMS value, pi by 3 VDC square by, this is VDC square by this whole square, VDC square by 9 during this period, and next 4 VDC square by 9, 2 VDC by 3 square by 9 during this period, and next here VDC square by 9 during this period, and take the average and take under root. This is the procedure for calculation of RMS value for symmetrical waveform. Now here if you simplify this one, the value phase RMS value equals to root 2 VDC by 3. So now what about the line voltage? This is VDC. So for the VDC here, so now same thing, this is the 2 pi, this is the pi. This is also symmetric waveform for this case also. So this one is the symmetric waveform. So for this case also, this one and this one up to here pi, this is 2 pi. This is square form. Square the waveform, take the average and take the under root, you will get the. So now here this value is 0 up to 2 pi only. So 2 2 pi by 3. This is 2 pi, this is pi. This is 2 pi by 3, this is pi by 3. 2 pi by 3 VDC square by take the average, so up to pi and take the under root. So this value equals to square root of 2 by 3 VDC. So now here we know the one relation that equals to V phase equals to root 3 of VL. Phase voltage equals to square root 3 into line voltage. So now this one, if you multiply with root 3 also, you will get the same value. This is line voltage formula and this one is the phase voltage formula. Now IT RMS thyristor current, same thing here, but here you need to take 2 pi value. Now that RMS value equals to VDC by 3Z. IT RMS equals to VDC by 3Z. Now what about for the star load? VL equals to root 3 V phase, that we derived root 3 VDC by 3. And what about the power? 3 into V phase square divided by Z. And for output power equals to same, if you calculate current square into R into 3. And for delta case, same, VL equals to V phase. And next case, root 2 by 3 VDC and V phase. So we derived, and same formula this one. We can substitute, these two are same. V3 VL square by Z, 3 VP square by Z. I hope all these concepts are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.